In this video, we are going to expand on our knowledge of Riemann sums that we have introduced in our previous video by looking at some examples and how the notion of Riemann sums can be used in practice. So the key idea, let us recall it, what we have made use of in defining the Riemann sums and making things work the way we wanted to work. So we had an integrable function f, which is defined on the closed interval ab. We were given a sequence of partitions, in fact, such that the mesh of Pn goes to 0 as we take in going to infinity. So then it said that upn minus npn goes to 0 as n goes to infinity, and furthermore in that case spnf, so which were the Riemann sums corresponding to the partition Pn and the function f, this also converges to the integral of f taken over the closed interval ab, and the convergence happens when n goes to infinity, as you have seen. Now, how do we make use of Riemann sums? There are two obvious ways of using Riemann sums in practice. So, suppose that we are given a sequence an, which somehow we can identify it with the Riemann sum or a Riemann sum of an integrable function f, for which the integral is known, and also the partitions for which the Riemann sums we have considered, that has the property that mu of Pn goes to 0 as n tends to infinity. So in such a case, we can compute the limit of the sequence an, which might not be very easy to compute otherwise. In the second case, suppose that we know that f is an integrable function and f is integrable on the closed interval ab, but somehow we do not know the integral. Then by defining the sequence an to be a Riemann sum corresponding to a given sequence of partitions and the function f, which satisfies the property that mesh of Pn goes to 0 as n tends to infinity, we can at least approximate the quantity integral fx dx. So let us see with some examples, with some concrete examples, how do we make these ideas precise. So suppose we were given with the following sequence. So what is the sequence? an is given by summation I equal to 1 to n I to the power r divided by n to the power r plus 1, where we can take this r to be a non-negative rational number. Now let us see if we can identify this sequence with a Riemann sum of some function which is known to be integrable and whose Riemann sums are known. So what do we do about it? So we can write this as summation as 1 by n summation I equal to 1 to n I by n whole to the power r. In this case, we can now get a very nice idea of the function. We can write it as summation I equal to 1 to n I by n whole to the power r and I by n so let me write it down. So I by n minus I minus 1 by n. Now you can think of the partition which we have already seen, a partition which divides the interval 0 1 into n equal parts, and so this partition gives rise to subintervals 0 1 by n 1 by n 2 by n etc, n minus 1 by n by n. So what is the length of these partitions? This length of the partitions are fixed. It is given by, so this is actually the length of the ith subintervals, and we can now associate this with a Riemann sum in the following way. So suppose we have this function f(x) as x to the power r on the closed interval 0 1. So this can be written as summation I equal to 1 to n f of ti I by n minus I minus 1 by n. So what are these ti's? Ti's are just the endpoints of these subintervals. Having done all this work, we can see that this is nothing but SPNF, where Pn is given by the partition which divides the closed interval into n equal parts. The tag set is given by taking the rightmost point of each subintervals, and fx is the function x to the power r. Now, is x to the power r integrable? Yes, it is, because we can also determine an antiderivative of the function. So we know that fx is x to the power r plus 1 divided by r plus 1 is an antiderivative of small f of x. And also the thing is that the function f of x, small f of x, is continuous on the closed interval 0 1, and as a consequence this function is integrable. So everything falls in place. The only one thing that we need to check is the fact that mu of Pn should go to 0 as n tends to infinity. But what is mu of Pn? It is the maximum of the length of each subintervals, right? So what is mu of Pn in that case? All the length of all the subintervals is 1 by n. So this is 1 by n. This goes to 0 as n goes to infinity. Now our key idea, the corollary that we have seen in our previous video, applies, and it says that this goes to integral 0 1 x to the power r dx. We know how to compute this integral. In fact, we know an antiderivative of this function f of x and this antiderivative is given by x to the power r plus 1 divided by r plus 1. So we can apply the fundamental theorem of calculus part 2 to get that this integral is nothing but f of 1 minus f of 0, which is equal to 1 by r plus 1. So this is how we make use of Riemann sums to compute limit of some sequences which is otherwise very complicated. You can imagine how would you compute this limit, but with the help of Riemann sums this was somewhat easier. So next let us look at one more example. So for example, if we could take the following one. Suppose we are given that an is the sequence summation I equal to 1 to n 1 by square root of n square plus in. So let us play the same game and write the equation in a form, write the formula in a form that we can relate it to, so that we can relate that form to a Riemann sum. Okay, so let's go ahead. So we have to take 1 by n out. Why do we do that? We always keep in mind that whenever we are working with this kind of a summation, we are somehow given this partition, which mostly we will consider throughout this course. So where Pn divides the interval into n equal parts, and what are the intervals? 0 1 by n, 1 by n, 2 by n, etc. n minus 1 by n, n by n, n by n. And in most of the cases we will choose our tag set to be equal to the endpoints of the interval. So now what are the length of the intervals? Length of the intervals is equal to 1 by n for each of the subintervals, and consequently mu of Pn, this is equal to 1 by n, which goes to 0 as n goes to infinity. And now let us try to see how do we go about it. So I take 1 by n out of the summation, and this gives me 1 by what do I do? I have to divide this thing by n, because n square, as I have taken this n out. So it looks like 1 plus I by n. And in a similar way, we could write it as summation I equal to 1 to n 1 by 1 plus I by n minus I minus 1 by n. Alright, so here this element corresponds to the value of fx at the endpoints. What is fx? Fx is 1 divided by under root 1 plus x. So if we choose our tag points ti to be I upon n, as I varies from 1 to n, then we get exactly this summation I equal to 1 to n f of ti. So ti's are the tag points I by n, which gives this value under root 1 plus I by n times the length of the intervals, which was originally defined to be as xi minus 1. So here we persist with exact values, and since mu of Pn goes to 0 as n tends to infinity, by our key idea, this sum converges to 0 to 1 f of x dx, which is nothing but 0 to 1 by 1 plus x dx. So under now, the only thing that I have forgotten to mention is that this function fx is actually integrable. This function is integrable. And how do we see that? Very easily. So we can see that this function is continuous in the closed interval, and consequently this function is integrable. Also, if you could argue that this function is monotone, but let's not talk about these things too much. But I hope you understand what I am saying. So this function, if also has an antiderivative, big F, where big F is given by f of x equal to 2 times under root 1 plus x. So by fundamental theorem of calculus part 2, this is equal to big F of 1 minus big F of 0. And what is the value? F of 1 is 2 root 2 and f of 0 is 2. So this is the answer. This is the limit of this sequence. You could have alternatively been given with a sequence bn, which is given by summation I equal to 1 to n, 1 by say n square plus I minus 1 times n. But in this case also, we would just, the exactly same argument will go through if we just choose our tag points to be the left endpoints of the intervals, and you can see the same arguments will continue to hold. So these two examples illustrate very nicely our first point, what we just mentioned, that if we were given a sequence an whose limit we might find difficult to work out. However, if we can relate those sequences to quantities like Spn f, where f is known to be integrable and also the integral of f is known, then we can compute the limit of an as n tends to infinity. Next, let me try to illustrate the second point with a small example, and we will finish the video with this. So what is our example? So suppose that we are asked to find the integral 0 to 1 dx by 1 plus x square. A priori we do not know what is this integral, what is its antiderivative of the function fx equal to 1 by 1 plus x square. You may say tan inverse x, but we have not formally defined what is tan inverse x in the closed interval 0 1. So we do not really speaking know what is the value of this integral, but we could do Riemann sums, and of course the partitions that we have been talking about, Pn, which divides the closed interval 0, 1 into n equal parts come to rescue, and we can make good approximations of this integral in the following way. So as we have seen that this partition gives rise to in subintervals of 0, 1 of equal length, and in subintervals of equal length, and we have also seen that mu pn is equal to 1 by n, which goes to 0 as n goes to infinity. And we can choose our tag set, so everything falls in place. And we also know that this function that we have taken 1 plus fx equal to 1 divided by 1 plus x square is integrable because the function is continuous. So everything falls in place, and we can apply our knowledge of Riemann sums to this example to make sure that we can at least approximate this integral that we want to work with. So how do we do it? We could choose our tag set to be either the first points of the subintervals, or alternatively, as we have been doing, we could choose them to be the endpoints of the intervals. So let us do it both ways and try to give you an idea. So suppose that here we have chosen a tag set, let us call it SI. uh, let us call it S, and S consists of points S1, S2, Sn, where we have chosen the last point. So Si is equal to I by n for I equal to 1 to n. And suppose that in the previous case we have our tag set equal to T1, T2, Tn, where Ti is equal to I minus 1 by n, and for I equal to 1 to n. So let me try to work out in what are the sequences that we are going to get. So here we are going to get an to be S, P and F. So it of course depends on t, so let us write t here in the subscript. And what is the sum? The sum is I equal to 1 to n f of ti, and of course I by n minus I minus 1 by n. This was in our definition xi minus 1, and we know how to simplify this. This will turn out to be 1 by n, which is independent of I, so we can take it out of the summation, and this is summation I equal to 1 to n. What was our function we have that we wanted to evaluate at this endpoints? So our function was given by fx equal to 1 divided by 1 plus x square. So this is nothing but 1 divided by 1 plus I minus 1 divided by n whole square. So if we simplify this will turn out to be 1 by n summation I equal to 1 to n square divided by n square plus I minus 1 whole square. And we know that this sequence converges to integral 0 to 1 by 1 plus x square dx, as we have seen in our theoretical result. Now what do we do here? Here we get the sequence Bn, which is of the form S, P and F, and let me write the set S as a subscript. So here also we play the same game, summation I equal to 1 to n f of small si, which is nothing but I by n, and we have I divided by n minus I minus 1 divided by n, and we know that this is 1 by n comes out of the summation I equal to 1 by n, 1 plus 1 by I by n whole square. Upon simplifying, this will turn out to be equal to summation I equal to 1 to n divided by n square plus I square. And we know that this converges to integral 0 1 by 1 plus x square dx. So in both cases, as n tends to infinity. So what is the upshot of this example? So we do not know how to compute this integral, but we can for each n compute this finite sums, you see. And and as we go and as we compute this quantities a n's, as n gets large, we get good approximations of this integral 0 1 1 by 1 plus x square dx. So with this we finish this video, which concerns about illustration of Riemann sums on how to use them in practice. Thank you.